Good morning. Hi, Victoria. Hope you're having a good morning. Sorry for the parent. It's early in the morning. I'm going to try to answer your question as concisely as I can. I made up 2 pages of notes, sent it along as a PDF file. So kind of follow that along as I go through this. Now, of course, some of this you probably know already, so I don't want to burden you, but the little notation P in anything simply means negative the logarithm of something. So pH simply means negative the logarithm of the hydronium concentration. Of course, you know already that pH is used to measure how much acid or how basic something is. For you, of course, it's going to be really important because it has a lot to do with blood chemistry and so forth. But that same P symbol notation can be used for anything. I have a little nerd there joke about the log cabin. You can take that for what you want. Now, this seems like a complicated way to express things, but actually it's pretty convenient. It's a way to take a relatively complex measurement like hydronium ion concentration and put it in a nice simple scale. Richter scale for earthquakes works the same way. The Richter scale is actually a logarithmic scale of the energy produced by an earthquake. So it's a way to take complex things and make them a little easier. But the same thing can be applied to everything. So I've got some examples there. You can have pH, which is negative logarithm of the hydronium concentration. You can have pOH, which is negative logarithm of the hydroxide ion concentration. You can also have pH or negative logs of various equilibrium constants. I'm not going to start talking about equilibrium constants. I assume you know a little bit about that. But pKa, for example, simply means negative logarithm of the ionization constant of an acid. pKb is the ionization constant of a base, and so forth. So you can do the calculations on there. You know a little bit about probably base 10 logarithms. You know, base 10 logarithm is a power you have to take a 10 to get the number. It's just the math. That's why God created calculators. So I've got some quick examples there that you know. The hydronium ion concentration of a solution is, let's say, 10 to the minus 10th. You stick that in the calculator. Negative the logarithm of 10 to the minus 10th is going to come out to 10. So the pH of a solution with 10 hydronium concentration of 10 to the minus 10th is 10. You can do the same calculation for a pKa. So if you have a solution or a substance that has an ionization constant of 6.8 times 10 to the minus 3, plug it into your magic calculator, it'll come out to a pH of, or a pKa of 2.17. Try that in your calculator. I'm sure your professor has given you all kinds of examples for you to work on and do what you want. So I'm pretty sure you get the idea there. That's drill and practice. That's just simple math. So what does this have to do with anything? Well, it has to do with water solutions. All water solutions, all aqueous solutions, contain hydroxide ion and hydronium ion in equilibrium because water ionizes to a certain extent. And for every water molecule, it'll produce one hydronium, one hydroxide. So there's a balance there. The more hydroxide, the less hydronium. The more hydronium, the less hydroxide. It's a constant. It's an ionization constant. Duh, that's what they call it, an ionization constant. So therefore, one way to express in any aqueous solution that the hydronium ion concentration times the hydroxide ion concentration is always equal to a constant. Turns out that constant is 1 times 10 to the negative 14th. That's known as the ionization constant of water. Well, another way to say this mathematically is convert those to logarithms, pH and pOH. So another way to say that exact same statement mathematically is pH plus pOH is equal to 14. Those two statements, the hydronium times hydroxide equals 10 to the negative 14th, and pH plus pOH is equal to 14 are mathematically identical equations, identical statements. Just a different way to say it. Now, the same thing can be done for pKa's and pA's. For aqueous solutions, the pKa and the pKb is essentially the same as the pH. So another way to say that is the the Ka times the Kb for any aqueous solution is going to be 10 to the negative 14th. Or another way to say that is the pKa plus pKb is equal to 14. Now, who cares about any of this? Well, the really critical thing about this, and the thing that will get you out of a lot of the problems that you have in tests and quizzes and so forth, labs, is that all you have to do is measure the pH of a solution, which is a pretty easy thing to do. You can do it with pH paper, pH meter, whatever. It's real, clinically, it's a very easy thing to do, measure pH. But once you have the pH, from that and knowing these mathematical relationships, you now can calculate the pOH, which means you can calculate the hydronium concentration, the hydroxide ion concentration. From that, you can get the pKa, you can get the pKb of a solution. And of course, all of this is important when you start discussing equilibrium of aqueous solutions, like blood is a very important solution, and buffers. And blood is a very complex buffer solution. So when you start trying to understand buffers and doing calculations of what buffered solutions are and so forth, saline solution is a buffered solution that you might give a patient or so forth. To calculate the composition of these buffer solutions or how to create these buffer solutions, you need to understand some of these calculations. So that's the short answer. I know it doesn't seem that short, but that's a pretty short answer for that. If you need to want a further discussion of this, and first of all, go to a lot of internet sites that can probably will do it better than I could, but you could try those, or give me a call. Obviously, I'm going fishing today, but I should be home after 5 o'clock, so I'll either give you a call and see if you got this message, or you can give me a call. Okay? Well, good luck.